object. One is weight passing through the center of gravity of the cylinder, and second is buoyancy passing through the center of volume of the displaced liquid, that is the immersed part. And both of them, by virtue of the symmetry of the cylinder, they are on the same along the same axis. So, and the two are equal, so it looks as if the object is in equilibrium. So, you go to the next level and ask, is it stable equilibrium? So, you tilt it a little bit. Now, this will require some geometric calculations to see how the center of gravity and the centroid of the displaced volume, how they move. But in case of a cylinder, you can almost anticipate. Let us say you rotate about the center of gravity. So, that G, point of action of G is the same, G meaning the weight. And the center of centroid of the displaced volume will shift leftwards. Okay. So, it creates a moment in the same direction as the rotation given, the incremental rotation you have given. The moment created, that means it tends to rotate the object even further. So, a cylinder that is floating with its axis vertical is said to be unstable. Okay, though in that exact position it is of course in equilibrium, it is in static equilibrium, but even a small displacement will create a moment that will tend to overturn the cylinder. You look at the other extreme of a cylinder floating horizontally and carry out the same let us say thought experiment. You will see that the rotation you give, it is not continuous rotation, small rotation through some small angle, maybe 0.1 degrees, okay, will create a restoring moment on the cylinder. Okay. So, the two are now opposed, which means that the perturbation tends to get cancelled off by the creation of a restoring moment. So, in one case it is a destabilizing moment, the other case it is a restoring moment. So, a cylinder floating on water is said to be, of course, it is in hydrostatic equilibrium, and the equilibrium would be classified as stable. Okay. So, this is an extra topic which has very important implications, like the book says, in naval architecture. So, it also gives an example of a huge ship. They kept loading it indiscriminately. At some point the center of gravity shifted, and relative to the centroid of the displaced volume, and the ship just overturned. So, that photograph is there in the book. Now, you might have read in the newspapers, something similar happened in the Mumbai dockyard just a few months ago. So, that ship it was just standing there, no waves, nothing. They just loaded the ship. At some point it just overturned. Okay. So, these calculate, of course, if it overturns, then it's massive damage. These, whether it is a cargo ship or a passenger ship, they cost a huge, I don't know how huge is huge for you, but I would say 100 crores is like the budget of this institute. That is the annual budget. That is the kind of money you lose, apart from not having the know-how of building a ship. So, it's a very major example. So, studying, but the principles are Straightforward. Okay, now if it's a huge ship, how do you find the center of gravity? So there you have to go to the first principles. Right? After all, this location is given as some ratio of integrals, right? And then how do you evaluate the integrals for an object where the mass is distributed, unevenly distributed? How would you evaluate that integral? Huh? We talked about it last time and we will talk about it next time also. These integrals are, you can't analytically evaluate them because that integrand is not known to you. How is mass, how are the boxes stacked in a ship? So some uneven arrangement. How will you evaluate the integral? Huh? Because you don't know the integrand in analytical or closed form. It's known to you point by point. So you have a 3D space and you know this box is kept here, that box is kept over there. And each box has its own weight. You have to convert the integral into what? A sum. Evaluate the integral as a sum. Okay. Over small discrete volumes. So big volume is equal to sum of small volumes. In each volume you know how much of matter is located. That's how you evaluate the integral and find the center of gravity. Okay. So this overturning of the ship happened even with what are the minor perturbations? It could be just a gentle breeze or it could be a small wave in the ocean. So small perturbations. If an integral is a sum, what is a derivative? Huh? It's just a quotient, it's a ratio of incremental changes, correct? The derivative, it's just the slope, so it's incremental changes. You take the ratio and that gives you the derivative. These are approximations because to get the analytical derivative, you have to take the limit of the increments going to what? 0. Right? So these are calculations to be carried out on a large scale. So I am just trying to mix and match some writing and some speech. Fortunately, we have a textbook in the background. The textbook also has unsolved problems. It also gives you the answers at the end of it. So I did that on purpose so that I could write straight away. The next topic, which is fluids in motion. So we have discussed. So see, in a course like this or any other course, we don't have an opportunity to repeat. Okay, so once it is said, it is said. So, but at the start of the semester, I'll try to repeat a little more often. So if the fluid is in a state of motion, then you know shear stresses are not 0. Okay? How do you connect shear stresses to fluid motion? Well, we discussed pressures. Okay. Pressure is force per unit area acting on a phase, any phase that you pick up in the fluid medium at right angles and is opposed to the outward drawn normal by convention. So, the shear stresses are given symbols. Well, one symbol that is given is tau. This is the Greek equivalent of T. Now, there are symbols and there are symbols, so just bear with me. These are shear stresses. Now, to understand the connection between shear and fluid motion, one of the earliest experiments carried out was by Newton once again, and this is called Newton's parallel plate experiment. So, as the name suggests, you have parallel plates and the fluid, which is liquid or gas, fills the gap between them, and the top surface is moved at some velocity u, and naturally it requires a force F. This gap is h. And Newton observed that A is the area of the plates, okay, in plane area. This is a plate, that plate has an area A, in plane area is proportional to capital U divided by h with a proportionality constant mu. Okay. So, this F over A, because that force F is applied parallel to the fluid surface, it is not normal. Normal would be equivalent to pressure. This is parallel to the surface, it is a shear stress. Okay. It is called a shear stress. This is how you can think of the application of shear stress. So, when you apply shear stress, the fluid is set in motion, and the velocity that is generated is capital U. So, I have shown here that the lower surface is held fixed, need not be held fixed, it can also be in motion, but in the original experiment it is held fixed, and you fill the gap with the liquid of interest or the fluid of gas of interest, and then this force turns out to be proportional to capital U over h. So, when you say it is proportional, it means the proportionality constant mu is independent of U over h. So, this mu is called dynamic viscosity, and more commonly just viscosity. So if anybody says viscosity, it means dynamic viscosity. And what is the dynamic viscosity? It's the proportionality constant connecting shear stress with the resultant ratio of u and h. You can't say it's proportional to velocity because h also plays a very important role. U over h. So they go as a combination. So why is that combination so important? Well, let's say this h becomes increasingly small. Okay. So now you are talking about a large flow field and you are looking at a small part of it. Okay. So the lower velocity, so if you just look at a small element, this phase may have a velocity component u along that phase, and then the top phase will have some velocity u plus delta u. So if you compare this situation with Newton's parallel plate experiment, you would conclude that tau will be equal to mu. See this, the area of that phase is now, it's combined with delta u. So this, how much is delta u? A small change in u, which we have been expressing in the past, like in the pressure variation problem. We wrote delta p is the derivative of p with z times delta z. Okay, so here it will be derivative of u with the y coordinate, okay, times delta y. The delta y goes away because you have that area factor. So this is the y direction. Okay, so we will revisit this expression, of course, not once, not twice, many times, but I thought I would connect shear stresses to gradients in velocity. That is very important, not velocity. I was trying to say that you should not think of force proportional to velocity. It is proportional to u over h. In more fundamental terms, it is proportional to the derivative of velocity with y, that is a velocity gradient. So Newton's parallel plate, the experiment is simple, but the conclusions that you draw, they become quite profound. Okay. So it's almost like saying Newton threw or saw an apple come down and discovered the law of gravitation. It just did a very simple experiment, but the conclusions are very significant. So suppose you have uniform velocity everywhere. Uniform is constant. Gradients are 0. There are no shear stresses, which means you are back to hydrostatics. Okay, so which is why over there we said an object in uniform motion, velocities are all the same, will not have shear stresses inside. It is still a hydrostatics problem. But now when you move to fluid motion, it's going to have gradients in velocity attached to shear stresses. Now, you can always ask, why should there always be a gradient in velocity? Can I not create a flow field where velocity is constant? Yes, you can create that flow field. In such a flow field where u is constant, shear stresses are 0, you don't have to treat it as fluid in motion, you treat it as hydrostatics. So hydrostatics becomes a special case of fluids in motion. Okay. Now the second observation of Newton is a little more restrictive, which is that mu is independent of the velocity u over h is velocity gradient. So, as we have just discussed, mu is independent of, that means even if you keep pulling the plate at extremely high speeds, still you will have a constant of proportionality. Now, experiments have been carried out, and it turns out that if you work with air, indeed it is true, mu is constant. If you work with water, indeed it is true. If you work with, let us say, salt water, it is true. Sea water, it is true. Oils, but here I should specify, I am referring to thin oils. Okay. It is true, but you go to thick oil. Thick oil is one with very high viscosity. Okay. This oil as found in nature, it's practically a solid. It's like clay. That is how it looks, and then it is processed, and you get this petrol, diesel kind of a liquid. At that stage, it is Newtonian, but in the initial stage, it is not. Which reminds me, clay also is an example of, it's a fluid-like because it tends to flow. But there are some intricacies, but you can think of it as a fluid in some context, because it responds to shear stresses. Blood does not follow this relationship in the sense mu is not constant. As you increase shear stresses or the velocity gradient, it tends to flow more easily, that is, viscosity goes down. Okay. So, this curve, that curve on the right hand side, depending on the choice of the fluid. So, it is a material property. So, dynamic viscosity is a material property. So, you may find the fluids where it goes down like that. You may find fluids where it goes up. Anything is possible. Okay. So, in that respect, Newton's experiment is not very emphatic about the behavior of dynamic viscosity. But if you think of air, water, oils, these constitute such a massive bulk of fluids or gases, whether it is helium, argon, nitrogen, all of them follow mu equal to constant. So, the pure abundance of fluids displaying constant viscosity makes this model, shear stress equal to mu times velocity gradient, very, very important. So, for such fluids where mu is constant, such fluids are said to be Newtonian. And sure enough, fluids that do not exhibit that behavior are said to be non-Newtonian. So, if you look at all possible fluids, most of them are non-Newtonian, but if you bring in their abundance, most fluids are Newtonian. In this course, we will work only with Newtonian fluids. So, I just said blood is not Newtonian. There are several examples in the book where it says, treat blood as Newtonian and proceed. Okay, so this graph is a straight line for a Newtonian fluid passing through the origin. That means when velocity gradients are 0, shear stresses are also 0. It's passing through the origin, though it doesn't, it made a small mistake there. So this is a Newtonian. Now what is the nature of viscosity? So I think we have discussed this point earlier, that microscopic features show up as macroscopic variables. So one of them was pressure. So viscosity also has its origins in the microscopic structure of matter, that we can look at later. But on the macro scale or the human scale, continuum scale, what is the impact of viscosity? Well, Newton, that the simple experiment, two plates, one moving with respect to another. So how do you create, how do you make such an experiment? Fixed plate is easy, it is stable, this is now a fixed plate. Right? This surface, and you want to have another surface move on it. Usually to demonstrate these principles you have rollers, and then you have one belt going down and coming up, moving that way. Okay, you neglect edge effects, then in the middle it is like this. The other experiment that is carried out is concentric cylinders. Okay, so the inner cylinder is fixed, outer cylinder is given rotation, or the other way around. Outer cylinder could be fixed, inner is given rotation. But how can a circular geometry approximate planar geometry? When will that happen? When the radii of curvature become very large. That means the gap R2 minus R1, let us say, becomes very small compared to R1 and R2. Then the circular arrangement approximates the planar arrangement. So now with the advantage with the circular arrangement is there are no edge effects. It's also very compact, just one shaft rotating. And you can make the gap as small as you want. Thanks to very modern machining techniques, you can produce gaps that are in microns, uniform gap in microns. And you can get it done for maybe 200 rupees, and you fill it up with maybe lubricant or water. Of course, it can also be air. Okay, but then viscosity of, it's almost imaginable that viscosity of air is much smaller than viscosity of water, which is much smaller than viscosity of oil. Okay. The difference is in a few orders of magnitude. One order of magnitude is a factor of 10. If I say 2 orders of magnitude, 100, and so on. Now, viscosity is independent of the velocity gradient, but it can be a function of other thermodynamic variables, namely pressure and temperature. Okay, for a pure substance, mu can be a function of pressure and temperature. Invariably, it's not a function of pressure, but shows a very strong dependence on temperature. Okay. So if you look at all the tables given to you, you will suddenly see it from a critical eye. You will notice that viscosity of water, for example, will drastically decrease even from 20 to 30 degrees. In this book, everything is 20 degrees Celsius. For us, everything is 30 degrees Celsius. Okay. And there's a big difference in viscosity for water, oil. For liquids, it goes down. For air, it goes up. Okay, so these trends depend on the microscopic structure of matter. Okay, so on the continuum scale, these are prescribed as material properties. Okay. So on the continuum scale, we are talking about forces, velocities, with parameters, namely viscosity, density in the background. Okay, density connects to pressure, viscosity connects to fluid motion. Okay. But of course, velocity will connect to forces, and forces will have shear stresses and pressure. Okay. So one more hidden message in this experiment, Newton's parallel plate experiment, which is the power required to keep the fluid in motion. That power required is just the product of force and velocity. You know, force times displacement is work done. The rate at which work is being done is force times. Force is constant, so displacement divided by time, or displacement differentiated will give you velocity. Forced, and they are in the same direction, F dot u, will give you the power required to sustain that motion. And how is the power expended? What happens to that power? Now that the fluid is set into motion, it's you're continuously spending effort, F times u. It will show up as internal dissipation in the fluid. Okay, so that F times u is dissipated by the fluid, and indeed you will see it as a small increase in the internal energy, namely temperature of the fluid, which is why see, if you have let's say if you have a lubrication system in, let's say, an automobile, this continuous rotation of the shaft will heat up that liquid. If you keep heating it up, its viscosity will go down and its lubrication capacity will keep going down. So you have a lubrication pump which takes out that hot oil and pumps in. You have to cool that oil, so you need a cooling arrangement for that oil, and then you put back oil at room temperature back into that shaft journal bearing system. So you have a very elaborate lubrication system. Okay. So this external work, which is F times u, is dissipated, which means viscosity is a measure of friction. And since we used the word internal pressure, the equivalent terminology would be internal friction in the fluid. So if you try to maintain a velocity gradient in a fluid medium, then you have to continuously spend power. So F times u would be like the product of shear stress and velocity gradient. Okay. So shear stress times velocity gradient is internal dissipation in the fluid medium that will appear as sensible energy, that means internal energy. Why sensible? There could be change of phase, but generally not. If you allow oil to boil, oil anyway is not volatile enough, but it may boil at some temperature. So the message is that viscosity is a measure of internal friction. In the fluid medium. Okay, so let's go to a new page. So we have learnt about pressure, we have learnt about shear stresses. But you realize that pressure acts normal to the surface. You have a surface, but in the surface changes, pressure acts normal to it. Similarly, shear stress, if this is the surface, shear stress acts parallel to it. If you pick another phase, it acts parallel to that phase. So the direction of the stress component depends on the choice of your phase. Okay, so that quantity, okay, so these in general shear stress, pressure you may call as normal stress. So, you can think of stress depending on the face on which it acts and its own magnitude. So, it is like a vector which has its own direction and a magnitude. In case of stress, you also have to associate it with the direction of the area on which it acts. So, there are two directions. So, to generalize, please return, Shashank is here, please return the biometric device to him. I think it is a good idea if you can get up, come around and place it here, while I continue. Okay. So, to integrate these terms, P and tau, we had two terms, but just to simplify notation, we use a single term. What is this symbol? Sigma. Okay. So, this sigma is given a symbol for stress, and because it depends on two indices I and j, I for fixing the face or the area on which it acts, and j for its own direction. So, it is geometrically represented So, I am showing a rectangular element. So, naturally we have Cartesian coordinates in the back of our mind. So, you can show the x and y coordinates. So, this vertical face, the one on the right, is an x face because the normal is in the x direction, and if I show sigma in the x direction, this becomes sigma xx. Okay, it is acting on the x face in the x direction. Okay, and but for this normal component we had used the term pressure, but that pressure was under hydrostatic conditions. Okay. So, now the fluid is in motion. So, it will not be just P, there could be other terms also, other contributions arising from the flow field. Okay. So, that is called sigma xx. So, you expect sigma xx to become minus P under hydrostatic conditions. And then we had tau. So, on this x face in the y direction, it is xy. Okay. So, you can similarly show, okay, so this is also sigma xx, this is sigma yy, sigma yy. So, this is sigma xy, this is sigma yx, y face x direction. Sigma yx. So, if you look at Newton's parallel plate experiment, this what is F over A? This is the fluid element, this is the fluid region. This would be, in terms of this notation, it is sigma yx, that F over A. Okay. And this sigma yx under one dimensional conditions, we said it is proportional to the derivative of u with respect to y. Okay. If you look at the other face, suppose you did the experiment in a vertical configuration, that would be derivative of v with respect to x. So, in general it is just the sum of the two. So, these details we will see as we go along, but this is the representation. So, let us say this is some point P in the fluid medium, and then this notation is given is called stress at a point. So, this is a Cartesian notation. You can have a similar notation in cylindrical coordinates. Suppose you go for 3 dimensions, then this rectangular element will become a cubic type or cuboidal element. Okay. So, I think in the book they use a matrix notation. So, sigma ij can be assembled in the form of a matrix with all the normal stresses placed along the diagonal. And off diagonal terms representing shear stresses. So, in 3D it is a 3 by 3 matrix. Now, doing 3D calculations are time consuming, algebraically complicated. So, I think almost all important concepts would be illustrated either through 1D examples or 2D examples. So, though I showed 3D here, rarely, I do not think in this course we will be required to look at a 3D example. You may be given a 3D problem where there are obvious simplifications and it becomes 2D. Okay. For example, there is a cylinder rotating and then an outer cylinder fixed. Okay. So, the gap, if it is uniform, then the velocity distribution will not change from one angle to another. So, the flow field is axisymmetric. So, there is no dependence on theta. Suppose it is very long, then there is no change happening from one z location to another. So, it is independent of z. So, this 3D example, real life example becomes just 1D in the radial coordinate. Okay. So, many problems can be approximated from 3D to 1. All real life problems are 3D, but we approximate them as 2D or 1D. 1D would be more common in this course. So, when the fluid is in, okay, now let us write down the equation for hydrostatics. So, in terms of the stress tensor, velocity is 0 or constant. So, I think in the book they say if the fluid has constant velocity, you let the frame move with the frame of reference, coordinate frame of reference, move at the same speed, then everything will look static to you. If I is not equal, no shear stresses, sigma ij equal to 0 if I is not equal to j. If I equal to j, then of course, it is minus p. So, this pressure originates from the microstructure of the material, of the fluid medium. So, it's often called thermodynamic pressure, okay, because you can estimate it from the equation of state, which is P over rho equal to RT for an ideal gas. For a liquid, let us say water, what is it? What is the equation of state for water over a normal range of pressures? density equal to constant, incompressible, that is the equation of state. Okay. Okay, so this is the background. Now, what did we do in hydrostatics? In hydrostatics, we set up a governing equation, okay, that gave us the pressure distribution. Once we had the pressure distribution, we integrated pressure to find forces and moments and points of action, okay, from pressure. So, the basic calculation was for finding the pressure distribution. So, you can call that equation that we had minus dP dz equal to rho g as the governing equation for hydrostatics. Okay. So, when the fluid is in motion, okay, when the fluid is in motion, we have to discover an equivalent system of equations, okay, like the one in hydrostatics. How did we set up that equation? By reference to a natural law. What is that natural law? That's Newton's law of motion. Sum of all external forces equal to 0. That was the natural law, applied to a part or a portion of the fluid medium, gave us the equation minus dP dz equal to rho g. So, starting point is the natural law. So, when the fluid is in motion, once again you rely on the natural laws. Okay. The natural laws are scale specific. If you are on a small scale, you have quantum mechanics. If you are at the human scale, you have Newton's laws of motion. And if you are on a very, 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 very large scale, it is a relativistic kind of a natural law. Okay. So, for our problem, for our set of problems for this course, we will set up equations. So, let us write governing equations. So, please complete this slide by writing governing equations of fluid motion will be based on the natural laws at the continuum scale. And from this point, we will continue on Friday. I do not see Shashank, which means he got back his 4 biometric devices. Yeah. Okay, thank you very much. In case you have a class, you can carry on.